Welcome to Architectural Insights with King KAMBUF.
It's great to be here.
We are diving into a stack of material today that feels less like standard industry reporting and more like a masterclass in professional acceleration.
It really does.
It's a daily digest tailored specifically for high-level, multidisciplinary experts.
Right.
This intelligence brief, which is sourced from the services of King KAMBUF PS Architecture's daily mentorship digest, is really the intellectual sparring you need to stay ahead of the curve.
And what's fascinating here, is the sheer breadth and the depth of the material we've synthesized for you.
It's pretty staggering.
We are moving, and pretty seamlessly, I'd say, from the macro-level global intelligence. We're talking using satellite data for city planning, adaptive structural grids.
Deep picture.
Huge picture. And then we go right down to the hyper-specific, microscale structural physics, the kind that governs failure modes and systems you might just assume are mundane.
Like what?
Like chilled beams. Or even the shelving in a rare book archive. Things you don't think about twice.
That's exactly why we call this a deep dive. Our mission today is pretty clear. We're going through this expert intelligence brief to pull out the most important nuggets.
And especially those aha moments.
Yes, exactly. Those moments that demonstrate a fundamental shift in how we approach the built environment. We're realizing that, previously external environmental factors—
things we used to just design against.
Right. Things like rapid heat fluctuations or subsurface soil saturation, even instantaneous air pressure changes. They're no longer just externalities.
No, they're becoming dynamic primary structural load cases.
That have to be anticipated and managed.
Yeah.
And in real time.
Precisely. We're going to look at some innovative projects where buildings literally breathe and adapt to their environment. We'll cover everything from geo-sonic seismic grids to responsive sensor adaptive foundations.
And then we're drilling down.
Then we're going to drill right down into the nuanced multimodal analysis that's required to maintain these high-performance, high-stakes environments. We'll explain why something like the slow process of humidity lag in an archive—
which sounds so niche.
It is, but it's critical.
Yeah.
Or why the frequency of vibration in a burning ventilation duct demands incredible specificity in your engineering analysis. The overarching theme here is converting environmental volatility into pure architectural intelligence.
Okay, let's unpack this. We have to start with the global view because the scale of adaptation that's being required is reshaping entire cities.
It really is.
The global pulse, highlighted in this King KAMBUF digest, emphasizes a massive directional shift. We're moving beyond standard, static design into real-time responsiveness.
And that's the key phrase, isn't it? Real-time.
It's all about integrating the building with the volatility of its surroundings, and in a way, turning infrastructure into a sensory organ.
It truly is the moment where the built environment stops being a passive barrier against the elements and starts actively, collaborating with them.
Collaborating, I like that.
Because if we can predict failure modes driven by environmental change, then we can design structures that compensate before those stresses become critical.
So the first core insight here is, for me, truly revolutionary in geotechnical engineering: dynamic foundations.
Yes.
The digest notes that Australia is leading pilot programs for slab-on-grade systems that are fundamentally no longer static elements. They're active, responsive interfaces.
This is an absolute game changer for foundation stability.
And it feels like a direct response to these increasingly unpredictable climates.
It's a direct, critical response to climate-volatile terrain. Specifically, you see this in regions plagued by swelling clay soils.
Ah, the classic problem.
We all know the cycle, right? When clay soils saturate after heavy rain, they swell. And that creates these immense upward expansive pressures.
And then the opposite happens in a drought.
Conversely, during periods of prolonged drought, they shrink dramatically. That leads to downward pull and often devastating differential settlement.
Which is what cracks foundations.
That's what destroys buildings. And traditionally, we just compensate for this volatility with, massive inert concrete structures or specialized, very deep pilings that try to ignore the near-surface soil entirely.
Just brute force it.
Brute force it.
But the innovation described here seems to tackle that instability head-on, right at the surface.
That's it. These Australian systems embed extensive humidity sensor arrays directly beneath the foundations.
So they're getting a constant data stream.
They're monitoring that clay soil in real time, not just once a year with a soil test, but continuously, 24/7.
That's the key technical upgrade.
It is. And here's where it gets really interesting. Instead of just compensating with more concrete, they actively adjust microvoids beneath the foundation slabs in real time.
Microvoid, so like tiny pockets of air.
Picture a controlled internal inflation system, almost like a smart air mattress under your house. If the sensors detect swelling clay pushing up, the system can adjust these microvoids to relieve that pressure locally.
Okay, and if it's shrinking?
If they detect shrinkage and the slab is starting to settle unevenly, they can manage the void space to prevent that differential movement. It props it up just where it needs it.
So the foundation's performance shifts from being a fixed, permanent element, just a heavy object sitting passively on the ground.
To a responsive, regulated system, a living system in a way.
This requires an immense amount of data processing, doesn't it? I mean, to
Yeah.
make those decisions second by second.
Absolutely. And that's why this is a geotechnical revolution driven by artificial intelligence in foundation response modeling.
The AI is running the show.
The AI models the rate of soil moisture change, it predicts the resulting stresses, and then it instructs the system on how and where to adjust the void pressure.
So it's turning a passive support element into an active, responsive interface with the ground.
Exactly. It ensures structural integrity precisely where the greatest environmental fluctuations are happening. And think about the other benefits. It saves on material, it reduces the need for overly deep and disruptive excavations, and it dramatically increases the lifespan of the structure in these volatile climates.
Incredible. Okay, so moving from volatile soil moisture to seismic volatility. The intelligence brief highlights major metropolitan areas turning their basic road infrastructure into these vast, distributed sensor networks.
This is infrastructure as anticipation. It's a fundamental change in philosophy.
So we were talking about implementing these geo-sonic municipal grids. The digest says they're being trialed in high-risk zones.
Right, primarily in places like Tokyo and Istanbul for obvious reasons.
And these aren't just your standard seismic monitors, are they?
Not at all. These are acoustic sensors embedded under the roadbeds, right underneath the existing asphalt and utility runs. And they aren't just waiting for a major earthquake to happen. Their purpose is far more proactive.
They were mapping tectonic microdrift. Can you elaborate on what that means for, say, an urban planner or an architect?
Of course. Microdrift is the tiny, almost imperceptible shifting of the Earth's crust that precedes major seismic events. Think of it as the sound of the Earth stretching before it snaps.
And the road network gives you the scale to hear it.
By utilizing the sheer density of a city's road network, which provides a vast, distributed matrix of acoustic sensors, the system can literally hear the Earth moving.
So the urban infrastructure effectively doubles as an early warning nervous system.
That's the perfect analogy. It's constantly forecasting the accumulation of internal structural stress across the entire metropolitan area, not just reacting to a major shock after the fact.
This fundamentally changes the relationship between a building and seismic data then. If the city knows microdrift is increasing stress accumulation in a specific downtown corridor, what's the architectural application? How did that change my design?
Well, that leads to the phenomenal conceptual leap that's proposed within the source material.
Which is?
Leveraging this real-time data to dynamically stiffen or relax a building's lateral systems.
You mean the building itself would react before the earthquake hits?
Imagine a high-rise tower that receives a 5-minute warning of predicted stress accumulation in its specific zone. It wouldn't just sit there and wait for the shockwave. It would activate its internal hydraulic dampeners or its active bracing systems in anticipation.
So it would pre-stress or relax key structural members to absorb the predicted energy.
Precisely. This is the high-level concept of an adaptive structure. It's moving us toward buildings that are seismically intelligent and predictive rather than just passively resilient. It's the difference between wearing a helmet and being able to dodge the punch.
That's a huge shift. Okay, let's talk about heat. The impact of climate-driven heat is clearly moving from being an isolated HVAC problem to a primary city planning and governance problem.
It had to. The old models are failing.
And sources say South Africa is pioneering a fascinating approach using satellite microthermal band data.
This approach is essential because passive cooling strategies are failing in many rapidly urbanizing high-density areas. This moves planning far beyond simply, mapping tree canopy or zoning for density.
And more granular.
Much more. They are dividing cities into what the digest calls heat risk parcels, or HRPs.
Heat risk parcels.
By analyzing satellite thermal signatures at a highly granular level, looking at material absorption and emissivity, block-by-block planners can predict exactly which areas will retain the most heat day after day, year after year.
This sounds less like architecture and more like, predictive public health.
That's because the application is profound. This process literally merges urban planning with thermodynamic epidemiology.
That's a mouthful. What does it mean in practice?
It means a high HRP, a high heat risk parcel, means higher predicted rates of heat stroke, respiratory illness, and a greater strain on public services.
And you can pinpoint this to specific neighborhoods.
You can pinpoint it to areas with less green space and more high-mass, dark surfaces. They are predicting health vulnerabilities block by block based on the thermal signature of the built materials.
So if I am designing a new development in a high HRP zone, the city might impose mandatory material and thermal performance requirements on my project.
Exactly. This raises a really important question for planners and policymakers globally. How does planning shift when temperature is no longer just a comfort metric, but becomes a legal, economic, or governance constraint?
So you could see a future where certain materials are banned in certain zones.
You could. Should specific thermal performance metrics be mandated for new development in a specific HRP? Should construction materials like pavement and roofing be regulated based on their thermal emissivity in these specific zones? It fundamentally changes the conversation around urban equity and climate resilience, and it makes the architect a key player in public health outcomes.
Wow. Okay, let's switch to energy. Energy storage is often treated as a peripheral utility, located in a dedicated facility somewhere out of sight. But the sources show Denmark integrating it right into the building core.
Which completely shifts the building's role in the grid.
How so?
Well, this integration is critical for stabilizing local microgrid behavior. This is essential as cities transition massively to intermittent renewable energy sources like wind and solar.
The sun doesn't always shine, the wind doesn't always blow.
Exactly. So Denmark's energy districts are integrating three-phase hydrogen storage modules, cooling phase, gas phase, and liquid phase directly into building cores, often in reinforced basement levels.
3 phases for hydrogen. That must maximize efficiency, I'm assuming. What's the function of the different phases within the architecture?
It maximizes both energy density and control speed. So the liquid phase gives you the highest density. That enables long-duration energy storage to ride out multi-day wind lulls.
So that's your backup.
That's your deep reserve. The gas phase offers a much quicker response and can be rapidly converted back into electricity via fuel cells.
For peak demand.
For peak demand. But critically, there's the cooling phase. The energy required to liquefy the hydrogen is itself managed.
So you're capturing the waste energy from the process.
You're integrating that cooling capacity with the building's own HVAC needs. You're turning waste heat from energy conversion into usable thermal energy for the entire district. It's a closed loop.
So instead of being just a consumer that draws electricity from the grid, the building becomes a dynamic energy buffer node. It's participating in the stabilization network for the entire local district.
Precisely. This level of integrated, multi-phase energy management means the architecture itself is a proactive, intelligent player in energy supply stability. It shifts the design mandate from just optimizing internal energy consumption to optimizing grid stability through multimodal resource management housed within the structure.
Okay, before we move on, the digest provides 2 great specific examples of engineering mastery applied to immediate environmental problems. First, air movement in São Paulo. We think of wind as natural, but this suggests it is becoming an engineered utility.
That's the core realization.
Yeah.
São Paulo is testing what they call morphable wind corridors.
Morphable.
These aren't just fixed lanes or canyons between buildings. They have adjustable canopy vents designed to modulate airflow based on real-time pollution readings. The objective is highly engineered.
What's the goal?
Actively reducing smog pockets and efficiently dissipating those stubborn urban heat islands by optimizing air mixing and movement across a dense urban surface.
It's designing a city that breathes on command.
Exactly. And it demands active sensors and control interfaces that can adjust huge elements of the urban landscape in response to atmospheric data. Urban airflow ceases to be a passive consequence of meteorology and becomes an actively managed utility.
Which requires a whole new layer of city management software.
A complex control system interface, yes.
And second, let's touch on material science. The use of microwave sintering for ceramics in Morocco. I get that cutting fuel use is great, but what does this do for the actual structural performance of the cladding?
This is a phenomenal materials science upgrade. By shifting from traditional gas-fired kilns to industrial microwave kilns, they cut traditional fuel use by over 90%.
A massive sustainability win.
Huge. But the structural benefit is paramount. The microwave process promotes incredibly uniform micrograin alignment, within the ceramic tiles.
Okay, what does that mean in layman's terms?
It means the internal structure of the material is almost perfectly ordered. This uniformity eliminates internal stress points and vastly improves the tile's structural integrity and its overall performance.
So the ceramic cladding is now stronger, lighter, and more durable against impact and thermal shock.
It is. And this detail, that sustainability must be paired with superior, verifiable technical acuity, is a non-negotiable principle in next-generation AEC intelligence. We aren't trading performance for green metrics. We're leveraging new processes to achieve both at the same time.
A really key point.
Okay, now we shift gears completely. The daily mentorship digest from KAMBUF contains these advanced study modules. They emphasize that seemingly minor specific factors, often overlooked in standard design practice, can become major structural or mechanical disruptors.
So we're moving from the macro scale volatility of the city.
Right down to the microscale physics of why things fail when they're stressed.
This section feels like a crash course in preventing highly specific engineering catastrophes. It's forcing us to redefine what we even consider to be a load.
That's a great way to put it.
Let's start with a common architectural feature: cantilevered balcony stacks in mid-rise residential buildings. The sources demand these undergo a rotational drift precedence check. For many designers, a cantilever is just a beam. Why is a rotational check so critical here?
Because stacked cantilevers are inherently mass-eccentric.
Meaning the weight is off-center.
The weight is jutting out from the main building core. Now, if you stack 10 or 20 of these vertically, you don't just add load. You create a cumulative torsional demand on the primary floor slabs and, crucially, on the main lateral resisting system, or the core.
A twisting force.
A powerful twisting force. During a seismic event, or even just high winds, that eccentric mass movement attempts to rotate the entire floor plate.
And if that rotational force isn't managed, what happens?
Well, if the lateral stiffness of the building isn't managed carefully across these successive planes, a concept we call diaphragm coordination, that cumulative torsional demand can simply overpower the entire lateral system.
So the building fails.
We call this torsional compounding. The rotations from one floor amplify the stress on the floor above and below it, leading to excessive displacement or cracking right in the core, where your connections should be most rigid.
I see the connection now. The source immediately relates this to terraced office complexes on sloped sites. What's the failure mode there? Is it the same principle?
It's the same principle, but amplified. Those complexes must model multiplane diaphragm rotation, because each level, sitting on a different elevation on the slope, forms a unique lateral diaphragm plane.
So they don't line up neatly?
Not at all. This creates stacked rotational vectors, meaning the rotational forces generated by a seismic event don't align cleanly from floor to floor. This torsional compounding generates incredibly complex internal shear stresses that require highly specialized hillside shear envelope modeling.
A level of analysis that's far beyond what you'd do for a standard flat site building.
Far beyond. It's not enough for your building to be stiff. You have to manage how that rotation propagates through the structure, or you risk tearing the building apart internally.
Okay, moving from structure to mechanical systems. Chilled beam office towers. These are known for being highly energy efficient, but why the specific focus on buoyancy-induced cross-floor recirculation? It sounds like we are fighting nature itself.
We are, in a way. Chilled beam systems cool air naturally, relying on the simple fact that cool air descends. They're passive and highly efficient, but they rely on predictable laminar air movement.
A smooth downward flow.
Right. The problem arises in high bay spaces, large atria, open-plan offices, lobbies, where you get warm vertical plumes.
From what?
From clusters of people, from equipment heat or intense lighting. These plumes rise rapidly.
So instead of the cool air descending smoothly, the rising warm plumes disrupt the intended flow. They fight against it.
They do more than disrupt it. They short-circuit the entire cooling efficiency cycle. They pull the warm air right past the chilled beams and redistribute it across the floor plate before the beams can properly condition it.
So the system is working, but the air isn't getting where it needs to go.
Exactly. Thermal buoyancy, that simple tendency of warm air to rise, becomes a critical mechanical system disruptor. It renders the highly efficient chilled beam system ineffective, which then forces the costly, high-energy supplemental cooling systems to kick on.
Wiping out all your energy savings.
Gone. The critical lesson here is that your airflow analysis has to treat temperature differentials as active forces driving flow, not just as passive states of comfort.
This is one of those insights that fundamentally changes a designer's perspective. Large-span auditoriums must verify air pressure flex loading on their roof membranes, treating air movement with the same structural gravity as a snow load. That sounds extreme.
It might sound extreme, but it's absolutely true, especially when you're dealing with large, unobstructed spans. Think about an auditorium or a sports arena.
Okay.
When the massive HVAC system adjusts rapidly, say during a ventilation purge or a major set point change after a performance, it can create significant, measurable pressure differentials between the vast interior volume and the exterior, or even between subvolumes within the space.
So that slight pressure difference acting over and roof the sides of a football field is enough to physically distort the membrane's curvature.
Precisely. That pressure differential, whether it's positive, pushing up, or negative, pulling down, acts as a quantifiable structural load case. It exerts a force across the entire surface area.
And over time, that causes problems.
If that membrane is flexible, even slightly, failing to account for this repeated flex loading can lead to membrane fatigue, sealant failure, or worst of all, drainage issues and pooling water over time. It confirms the principle. Engineered air movement has to be treated with the same structural discipline as wind or seismic loads.
We're back to the ground now, focusing on river-adjacent civic structures. The requirement here is for differential settlement shear band profiling. This sounds incredibly complex. What exactly is a migrating shear plane?
This is civil engineering knowledge that's being elevated by recognizing environmental cycles. Near rivers, lakes, or tidal zones, the soil's moisture content changes constantly. You have seasonal flooding, drought, river level changes.
Rivers of floods.
Always. That variable moisture content introduces inconsistent load-bearing capacity, and crucially, it creates inconsistent shear bands deep below the foundation depth. A shear band is simply the layer where one segment of soil slides relative to another.
So settlement isn't just a slow, uniform sinking over 50 years.
Not at all. Settlement is rarely uniform in these dynamic hydrological conditions. Instead, the shear planes, those internal sliding points, they migrate cyclically with the soil saturation and moisture content cycles.
So they move around.
You get one layer pushing here during the wet season and a different layer pulling there during the dry season.
Can you give us an analogy to make that complexity a little more understandable?
Think of it like trying to build a tower on a giant unstable layer cake. Or maybe a stack of Jenga blocks where the layers are constantly shifting their friction based on how wet they are.
And that internal movement causes differential settlement.
Meaning one corner of the foundation sinks faster than another. Identifying and profiling these migrating shear bands is essential for designing robust, deep foundations in these environments. If you miss them, the cyclic stress will eventually crack the foundation system itself.
Another thing you don't think about. Fire safety is standard practice, but the digest specifies modeling fire-induced vibration pathways in hospital mechanical floors. Why model vibration? We usually just focus on heat, smoke, and suppression.
This really speaks to the complexity of a fire event. It is far more than just a thermal problem. Consider a fire breaking out on a mechanical floor, which is dense with equipment and, critically, heavy ventilation ducts.
Right.
The intense, rapid heat causes these large metal ducts to heat up and expand very rapidly. This thermal stress induces mechanical vibrations and oscillations within the ductwork.
And those vibrations transfer directly into the structural frame of the hospital.
Exactly. The ducts act as conduits. They efficiently transfer this high-frequency mechanical stress directly into the structural frames.
So a fire event is multimodal.
It's thermal, the heat and smoke, it's acoustic, the noise and vibration. And it's mechanical. It's stressing the structure. Designers have to model these secondary mechanical effects to ensure that essential structural elements and, more importantly, surrounding life safety systems.
Like emergency power conduits or water lines.
Exactly. They have to remain functional and intact during and after the initial thermal event.
Here's a deeply nuanced scenario from the digest. Split-zone libraries with rare collection stacks. The required check is the analysis of cross-humidity lag. This seems like a detail that's only relevant to the most sensitive projects. Why is it a point of failure?
It is absolutely critical, and it's fundamentally a time-dependent problem. It really highlights the difference between static design metrics and dynamic environmental response. Rare collections maps, manuscripts, old books, they require extremely stable environments. That means precise temperature and humidity set points.
But if the building has two zones, say a fluctuating public reading room and a sealed archive, That transition zone between them must be the critical point.
It is the critical point. If the humidity transition is too rapid, or if the lag time for the HVAC system to adjust is too slow between these zones, it severely strains the organic materials.
What kind of materials?
Materials like wood shelving, antique paper, and critically book binders, they're all hygroscopic.
They absorb moisture from the air.
They swell and contract based on the moisture content. If that change happens too quickly or unevenly across the thickness of a book spine or a shelf, you get warping, cracking, and material degradation.
So the error isn't hitting the right humidity percentage, it's hitting it too fast.
That's a core realization the digest is pushing. Humidity equilibrium is fundamentally a time-dependent material compatibility issue. Most building codes, they design for a specific humidity percentage, say 50%. Next-generation design must design for the rate of change the materials can tolerate over time.
The speed of the change matters as much as the change itself.
It matters more in some cases. If the temperature drops quickly, demanding rapid dehumidification, the material needs time to adjust, or you risk irreparable damage.
Okay, finally in this section, transportation hubs, specifically multi-platform transistors. The requirement is to analyze micro-pressure drift zones. This seems like a really abstract layer of physics.
This is pure physics in motion, and it's all about safety and air quality. When a heavy train moves into or out of a subterranean station, it acts like a giant piston, pushing and pulling air.
I can picture that.
This creates alternating high-pressure pushes ahead of the train and significant low-pressure pockets, the micro-pressure drift zones behind it.
And how does that momentary pressure differential affect the infrastructure? What's the risk?
It directly affects the ventilation system's behavior, particularly during an emergency. The low-pressure pockets can disrupt the designed airflow patterns. They can potentially pull contaminated air or smoke across platforms from adjacent tracks rather than pushing it out as intended.
A huge life safety issue.
A massive one. It also stresses the HVAC equipment itself. It requires cross-platform pressure mapping and specific HVAC response timing. The systems need to anticipate when a train will move, using scheduled data and platform sensors, and instantly adjust dampers to maintain stable air quality and ensure emergency exhaust routing remains effective.
So the train schedule itself becomes a crucial piece of the mechanical engineering specification.
It has to be.
Okay, this section of the KAMBUF material is where all that deep physics meets the immediate high-pressure world of construction management and rapid problem solving.
The real world.
These scenarios show exactly how design intent often encounters the messy reality of site conditions and, unforeseen adjacencies.
These are excellent case studies because they focus on diagnosing a real-world, unexpected problem, identifying the physics behind it, and then implementing a rapid, multi-step workflow correction under some very tight constraints.
Let's look at the data vault scenario. We have a below-grade vault experiencing what they call a thermal pulse influx, a rapid, shocking heat spike of 14 degrees Celsius in under 90 minutes.
A huge spike.
And the cause. An adjacent furnace exhaust duct was rerouted too close, hitting a peak temperature of 92 degrees Celsius near the vault wall.
And the critical data point here is the mismatch between the external influence and the internal tolerance. That vault-sensitive electronics can only tolerate a 3-degree Celsius fluctuation.
So a 14-degree spike in 90 minutes is?
It's a condensation and catastrophic electronics failure event waiting to happen. The initial R15 wall insulation was judged completely insufficient for this kind of high-temp adjacency.
And this is not a peak temperature failure, it's a rate of change failure.
Right.
So what was the mandated step-by-step workflow solution?
It required a multi-layered defense to address both the speed and the magnitude of the heat transfer. Step 1. Immediately add thermal baffles between the vault wall and the redirected duct to break that direct radiant heat pathway.
A quick fix.
A necessary first step. Step 2. Introduce negative pressure microventilation loops to actively cool the small interstitial space that is formed between the duct and the wall.
So you're actively cooling the outside of the vault, rather than just trying to cool the inside more.
Precisely. You attack the source. Step 3. Upgrade the passive resistance by replacing the R15 insulation with composite high-temp R30 panels. This addresses the magnitude of the heat.
And then the smart stuff.
Steps 4 and 5 involve the intelligence component. Install heat pulse dampers that are triggered by rate of change sensors. This is crucial. You're not just reacting to the 92-degree peak temperature, you're reacting instantly to the speed of the temperature increase, which is the actual risk factor here.
And the final step.
Finally, you have to recalibrate the humidity control algorithms because that rapid temperature spike will cause moisture to condense on all the internal equipment surfaces.
The key lesson is that thermal risk is temporal.
It is. The source explicitly states that heat events demand temporal analysis, not just peak temperature evaluation. An instantaneous high heat source is far more dangerous than a slow, steady increase to the same peak temperature because the building materials and the HVAC systems have no time to equilibrate.
Right. Okay, next scenario. A performing arts center reports intermittent pressure pop sounds in the curtain wall. This happens specifically during rapid temperature drops, 18 degrees Celsius in 40 minutes, right at dusk.
And you can imagine you're trying to watch a performance and the building itself is making noises.
Interrupting the show.
That audible pop is the structure warning you of imminent failure. This is a textbook example of a thermal inertia mismatch manifesting as an audible mechanical event.
So what was happening?
The diagnosis showed the rigid components, particularly the mullion expansion capacity, were maxed out. Microbending was occurring in the glazing clips. The frame and the glass were stressed because they couldn't accommodate that rapid thermal contraction during the sunset temperature drop.
And the risk is high.
A very high risk of glass stress fracturing and failure.
What was the rapid-fire fix for this complex thermal stress problem? How do you even start?
The workflow begins with a deep diagnostic dive. You perform rapid delta thermodynamic modeling of the mullion assemblies to understand exactly where the stress concentrations are occurring during that fast cool down.
Then the physical fixes.
Then come the physical fixes. Introducing micro-expansion slots at the mullion anchors to allow for greater controlled movement and adjusting the glazing clip tension to reduce the preload stress that contributes to that popping sound.
And how did they address the speed of the temperature change itself? Slowing the gradient seems vital here.
That's the intelligent intervention, adding phase change insulation behind the mullions.
How does that help?
Phase change materials are revolutionary here because they absorb and release heat during a phase transition melting or freezing, and that effectively slows the rate at which the temperature gradient passes through the assembly.
So it gives the mullions time to adjust slowly and safely.
Exactly. And finally, deploying nighttime pressure relief venting at the upper zones helps to balance the pressure differentials created by the cooling air inside the building, which reduces the load on the curtain wall assembly.
The key lesson here is immediate. Curtain wall acoustics are not just an annoyance.
They signal a serious structural problem caused by thermal inertia mismatches.
Okay, the last practical bite focuses on life safety. Specifically, NFPA 72 voice evacuation systems. The source emphasizes this is not just about installing some speakers. It's a detailed computational challenge.
Absolutely. The source frames this as a problem of computational sequencing and psychoacoustic intelligibility.
What does that mean in practice?
Code dictates that intelligible directives, meaning clear enough to be understood under duress, must transmit across the entire zone within 10 seconds of activation. This demands incredible computational speed and precise management of the sound waves in complex architectural spaces.
And what about multi-zone spaces, like large office complexes or transportation hubs?
Multi-zone spaces require overlap suppression. You cannot have competing voice messages confusing occupants who may be moving between floors or departments during an emergency. The system has to know exactly which zone is active and suppress any overlap instantly.
And the tones themselves matter.
Furthermore, the pre-signal tones, often electronic chimes or warnings, they must meet ADA psychoacoustic clarity requirements. These systems have to be designed for maximum cognitive recognition and clarity, especially for those with hearing impairments or who are under extreme stress.
So the engineering challenge is merging high-speed sensor activation with complex computational audio clarity.
All to save lives.
Right.
So after diving into all that technical acuity, the deep physics of stress and volatility, the KAMBUF Mentorship Digest challenges us to lift our heads up, to apply this knowledge to highly ambitious conceptual design.
This is the fun part.
It is. The philosophical question posed here is, how do we take environmental volatility, all the heat shocks, seismic drifts, and tidal movements we just discussed, and convert that complexity into architectural intelligence and physical expression?
This moves us into the truly visionary realm, using the physical manifestation of architecture to express otherwise invisible environmental data, essentially making the building a public sensor readout.
A living instrument.
The first conceptual challenge is the Atmospheric Registry Pavilion. It's a public pavilion tasked with recording atmospheric signatures like ozone levels, particulate matter, and seasonal temperature deltas.
And the constraint is what elevates this from art to engineering.
No screens.
No screens or digital displays are allowed. The environmental data has to be expressed architecturally through physical transformations of the interior volumes.
So what would that look like?
Imagine walking into a space that subtly contracts or expands its ceiling height based on atmospheric triggers. The internal volume literally changing shape to reflect poor air quality or high ozone outside.
That demands that the architect design with responsive materials, active kinetics, and complex fluid mechanics. It makes the building a kinetic sculpture driven by data.
It does. And it has to be operable year-round and must include at least one passive mechanical system.
Meaning the structure itself must be performing the measurement and the expression simultaneously.
Right, through solar, thermal, or wind energy. This challenge forces designers to think beyond just cladding and floor plate and consider the volumetric behavior of space as a direct output of environmental data.
So if the form changes to reflect increasing ozone levels, the architecture is actively participating in the civic discussion about environmental health.
Without needing a plaque or a display screen, the building is the message.
Okay, next we have the Civic Resonance Harbor, a waterfront civic building whose structural framing must visibly respond to multiple water rhythms.
All of them. Tidal cycles, atmospheric pressure, even rapid boat wake frequencies.
This is a step up in complexity because the rhythms are disparate. You have the slow tides and the fast boat wakes.
And the deliverable required is a structural diagram showing variable response framing zones tied to these environmental rhythms. Think about a passive kinetic element within the structure. Perhaps specific cross-bracing members that gently tension or relax depending on the water level or atmospheric pressure outside.
Driven by smart hydraulics or pneumatics,
Exactly.
it's designing a building that literally breathes with the water, giving the public a visual, palpable sense of the environment's dynamic forces.
But the difficulty lies in ensuring accessibility and stability while allowing the structure to kinetically express these fluid forces. The building has to maintain absolute stability during tidal extremes and major storms, yet still incorporate a visible, passive kinetic element that performs a constant environmental status check.
So it integrates the structure not just as a static defense against water,
But as a visual, resonating participant in the hydrological system, it's reminding us of the immense forces we build against every day.
finally, the highest level of synthesis, the role of architecture in governance. The Digest identifies an RFP for the Great Lakes Cross-Border Flood Diplomacy Center in the Detroit-Windsor Binational Zone. This is where high-level policy meets deep engineering.
This project, a research and governance complex, has a truly massive scope. Its mission is coordinating flood risk data, harmonizing hydrological policy, and unifying emergency response between the U.S. and Canada.
So it's the purest example of architecture as governance infrastructure.
It is. It's a building designed to facilitate diplomacy and policy that's rooted in shared environmental data.
So it requires blending deep engineering foresight. It needs to house watershed modeling and wetland simulation labs with high-level public administration and civic architecture, all under a binational mandate.
And the proposed angle in the brief is essential, to frame the architecture itself as a binational hydropolitical interface. The form of the building must actively help visualize shared flood futures and cross-border responsibilities.
How would you do that?
This could be achieved through shared, transparent data walls that display joint risk assessments, or through a design that visually and physically bridges the two nations. The architecture is not just a container. It is physically and conceptually coordinating complex policy decisions regarding shared water resources and shared climate risks.
It's the ultimate synthesis.
It requires the deepest possible synthesis of technical skill, engineering foresight, and diplomatic sensitivity.
Wow. We covered so much ground today in this deep dive into the architectural insights with KAMBUF Daily Mentorship Digest. From geo-sonic mapping in Tokyo and the complex physics of torsional compounding,
To thermal dampers in data vaults.
and the conceptualization of binational architecture for flood control. What stands out to me is the recurring theme, and it's loud and clear. The environment is no longer outside the building. It is a dynamic, integrated, and volatile load case that we have to design with, not just against.
That is the core realization, and it carries immense weight. If we connect this to the bigger picture, the distinction between architecture, engineering, and environmental science is rapidly vanishing.
Emerging.
The most successful multidisciplinary designers of the future won't just design for passive stability, they will design with volatility. They will leverage dynamic systems, rate of change sensors, and active foundation coordination to turn environmental stress into actionable intelligence.
We encourage you to reflect on the core questions posed in the source material. These are not just arcane technical problems. They are philosophical and functional challenges for the entire built world. Understanding these mechanisms, the migrating shear planes, the thermal pulse influx, the need for temporal analysis, this is the baseline for next-generation mastery.
And this raises an important question for you to mull over as you integrate these insights into your own practice. And that question is, how can my buildings anticipate thermodynamic fluctuations as proactively as they anticipate structural loads?
That's the key.
That fundamental shift from designing for passive static stability to designing for proactive, informed anticipation is undeniably the next frontier in the architectural profession.
Thank you for joining us for Architectural Insights with KAMBUF. Keep building your knowledge base and keep designing for a dynamic future.